The Kc value for this reaction is 4, 2, and it's 2A plus B2 gives me 2AB. They tell me that it is a exothermic reaction. I know it's exothermic because delta H is less than 0. How can I increase the value of Kc? In other words, increase this 4.2. So the only thing that changes Kc is a change in temperature. So either we want to increase or decrease the temperature. If we want to increase the value, we want to favor the forward reaction. So we're trying to favor forward. How do we favor forward? Well, that means that we want to favor the exothermic reaction. How do you favor the exothermic reaction? You lower the temperature. Looking at the options that were given, you cannot do anything with pressure. You cannot do anything with pressure, and you had to lower the temperature because it favors the exothermic reaction. You've got a Kc value over here, and if you want to work it out, you have to say that Kc is equal to the concentration of the product, which is Hi, raised to the coefficient of the number in front of it, divided by H2 and I2. They give me some concentration, so all I need to do is substitute in. It's 10,6. I need to square that, divided by 1,2. I didn't even have to write it. I don't have to do anything. I literally just have to substitute those values in, and I land up with 66,9, which is A. Calculate the value of the equilibrium constant for the reverse reaction. All I need to do for the reverse reaction is it's 1 over the Kc of the forward, and that means that I just go 1 over 66,9, and I land up with 0,015. What effect would an increase in pressure have on the yield of this particular reaction? Well, I have got 2 gas moles on the left and 2 gas moles on the right, so pressure is going to make no difference. So no effect is my correct answer, but why? Because only temperature changes the equilibrium position? No, only temperature changes the Kc value. The reason that this one doesn't shift is because they are the same number of gas moles on both sides. What effect will an increase in pressure have on the value of the equilibrium constant? Again, only temperature changes Kc, so no effect is the correct answer, but I now need to look at why. There are the same number of moles on both sides is not the reason that it's not going to change Kc. The reason that it's not going to change Kc is because only temperature changes Kc. So my correct answer there is going to be B. At 400 degrees, it was found that the value for the equilibrium constant was 41. Use that information to determine whether that reaction was exothermic or endothermic, and we're still talking about the previous reaction that was given to us. The Kc value decreased from 67-ish down to 41. So let's see. When I increase the temperature, I favored the forward. Sorry, I favored the reverse because I decrease the Kc. That's reverse, and that's because decrease in Kc. Then you need to say that a temperature increase will always favor the endo, and therefore the reverse must have been endo, and therefore the forward must have been exo. So what do they say? Use the information given to determine whether the reaction is exo or endothermic. So it's exothermic, so it's one of those two. And high temperature always favors the high temperature favored the reverse reaction, and therefore the forward must be exothermic. So you need to look at all the details that are given in these choices. Here we've got a nice little graph, and they tell me values that are placed inside, and they put a certain amount of CO, Cl2 in, and it splits up into carbon monoxide and chlorine. My delta H value is positive. Let's see what's going to happen. Use the graph and the equation. How much time was required for the system to come to equilibrium for the first time? If I've got moles on the left-hand side of the axis over there on the y-axis, I land up, equilibrium is when the number of moles remains constant. So the first time it remains constant is at 30 seconds. How do the rates of the forward and reverse reactions compare at 75 seconds? So if I take a look at 75 seconds, it's over there, I can clearly see I'm getting less of the Cl2 and CO, they're both going downwards, and I'm getting more of the COCl2. So in other words, at that point, the reverse reaction is being favored, so that means that the reverse is greater than the forward. How do the rates of the forward and reverse reactions compare at 165? So let's go to 165, and there we're at even keel, so they are equal to one another. And how do the rates of the forward and reverse reactions compare at 15 seconds? As you can see, the forward reaction is increasing because I'm getting more and more of the Cl2 and CO. And the reverse reaction is decreasing. Why? Because I'm getting less and less of the COCl2. So the forward reaction is greater than the reverse. Explain why the number of moles of each of the species in the mixture changed between T45 and T105. So in other words, I'm taking a look at this section over here. We can clearly see something happening over there, and that is a whole lot more chlorine was added to the system. So that's the only option. The others are wrong. Chlorine was added to the system, so the equilibrium favored the reverse reaction. Why? Because we wanted to move away from the chlorine and we wanted to go back to the COCl2. At T120, chink, something or other happened. What was it? The piston was pulled outwards and the volume was doubled. The reaction quickly reached equilibrium again at the same temperature. Using the data for T2 to 5, so in other words over there, no, over there, sorry, Kc is calculated at 0.31. What was done at 180 seconds that can account for a change in Kc? Well, it must be a change in temperature. Unfortunately, they've told us that all of them are a change in temperature, so that's inconvenient. And change the number of moles, and you have to somehow explain that answer. So we need to consider whether this was an exothermic or whether it was an endothermic reaction. So what have we got happening? The first thing is that the Kc changed from 0.2 to 0.31. So therefore, oh sorry, no, it's not 3.1, it's 0.31. So therefore, at 190 seconds, we must have favored the forward reaction. How do we know that? Because if we take a look over here at 190 seconds, I'm getting more of the products and less of the reactant. So we favored the forward reaction. The forward reaction, according to the previous page, was an endothermic reaction, because the delta H value was a positive value. It was positive 109 kilojoules. And therefore, what does that tell me? It tells me that the endothermic was the forward reaction, which was favored, and therefore endothermic is always favored when we have got an increase in temperature. So let's see what we've got. Temperature must have increased. Temperature increase, so not the decrease, due to, and it must have favored the forward reaction. That seems reasonable. So A is your correct answer. New reaction, we've got N plus O2. The value of the equilibrium constant for this reaction is 1,5. What will it be for the reverse reaction? Remember, it's just the inverse of 1,5, which means that you land up at, I think, 0,66. Change in the value of the equilibrium constant for that particular reaction is given in the table. The reaction takes place in a closed container. Is it an exo or an endothermic reaction? Well, what we can see is that an increase in temperature favors the forward reaction. How do I know that? Because as the temperature goes up, my Kc value goes up. An increase in temperature always favors the endothermic reaction, and therefore the forward reaction must be an endothermic reaction. So a high temperature favors the forward reaction, and therefore it is endothermic is my correct answer.